Okay, so we are starting with example number 1 of section 12.8. It's a platform rotating, right, such that at any instant its angular position is described by theta equals 4t to the 3 half. And then we have also a ball rolling down a groove, and the ball goes outwards, and its position is r equals 0.1 t cubed. I wrote right here the expression for velocity and acceleration for cylindrical coordinates. Why are we using cylindrical coordinates? Because we are given the expression of the rotation in terms of theta, and we are given the expression of the relative position of the ball respect to the platform in terms of r. So it's very easy for us to use our coordinate system will be r, theta, and c. But this ball is not moving in c, so if we wanted to include the c direction, we would have to include c dot theta c, and here c two dots c, right? But since the ball is not moving in that direction, well, this c will be equal to 0, and this c two dots will be equals to 0. So we will have only velocity in the theta direction and in the r direction. So if we look at the trajectory of that ball is moving around the platform, and it's going outwards. So it will be like a spiral, so to say, something like that, right? So, and we are asked to find the magnitude of the velocity and the acceleration for a specific time. So let's write here the solution. We have to find the expressions in terms of what we have right here in terms of those equations. Here the equations are given in terms of rho, and our data is given in terms of r, but that's just a different variable. But we need to know that rho means how the ball is going outwards respect to the center of my coordinate system. So we have theta, which is 4 t to the 3 half, and then we want to find theta dot, because that's what we need here. So the derivative of that will be 4 times 3 half, 3 times 1 half, right? And that's equals to 6t half. And then we want to find t2 dots, so we have to derive this expression, and that will give us 6 times 1 half times to the minus 1 half, right? So it's 3 2 times. We can put it very organized. 4 3 to the half, theta dot, it will be 6t half, and 2 dots will be 3 to the minus half. And now we need our rho, which is given by that r, so we can say that rho is equals to 0.1 times to the cube. Then we have rho dot will be 0.1 times 3t squared, which is equals to t. And then we got rho 2 dots that we also needed right here. Actually, let's write these expressions all in terms of rho, because we have to be consistent with our the variables that we use. And then we have, this is the second derivative of that will be 0.6 t. Write that here. So rho will be 0.1 t cubed. So I just want to be organized, because it's very important to find out if we made a mistake or anything. When we have the data organized, we find our errors or our mistakes much easier. So those are our variables that we will plug in here. But before we plug that in here, we need to find at what time do we want to calculate those variables. And time is equal to 1.5 seconds. So for t equals 1.5 seconds, I have those variables calculated, so I'm going to copy them. Theta is equals 2, so plug in 1.5 here, gives you theta is 107.348 radians. Theta dot has the same value, you can calculate that. And theta 2 dots which is the acceleration, right? Is the angular acceleration of the platform is 449 radians. So this is over seconds, and this is over seconds squared. So we calculate rho for that time. So we'll plug on 1.5 over here, and we get 0.3375 meters. Rho dot is equals to 0.675 meters over seconds, and rho 2 dots is equals to 0.9 meters over seconds squared. We plug all these values in these formulas, and then we get that the velocity is equals to rho dot 0.75, right, in UR plus R 0.3375 times theta dot, which is 7.348. That's in theta direction, right? And since I'm calculating the velocity as a vector, we got m over seconds. We have to multiply those two values and get the result. This value is already the same. U direction plus 248 u theta. This in vector form, if we want to calculate the magnitude, we know that we have to square each of the terms. So if you remember that the magnitude will be V equals square root of that expression square, right? So we can write the results, and the velocity will be 2.57 meters over square. This is the magnitude. To calculate the acceleration, we do the same, very easy. So we just plug or our variables that we calculated into our formula. So you have to review. It's very important to understand where this formula comes from, and we did that in the theory, right? So will be rho 2 dots minus, this is rho as well. Just use the same variable for the whole equation, very important, right? To be consistent. And this is 0.3375 times theta dot square. That's in the direction, R direction, plus 2 times rho, which is 0.3375 times theta dot, which is 7.348, plus rho again, 0.3375 times theta 2 dots, which is 2 times 449. And that's all in the u theta direction. So when we calculate that, we get minus 17.33 in the u direction, in the UR direction, right, in the direction of R, and plus, let me make it that clear, this is R, plus 10.75 in the theta. And all that is in meters over second square. So that will be the vector expression of the acceleration, where we have two components. We have the R component and the theta component. We do not have C components, as I said. We don't have motion in C direction. And we can calculate the magnitude using the same formula, you know. This formula, well, that gives me the same formula, but now using the acceleration, give me the magnitude. So if I plug those two values in here and square the values, I get the acceleration in magnitude is equals to 20.4 meters over square. So that it gives us where we were being asked the magnitude and the velocity, the magnitude of the velocity and the acceleration for the valve at t equals 1.5 seconds.